So we're going to have a look at how our understanding of the atomic model that we currently use was arrived at and was created. So we're going to go back basically to the birth of what we describe as modern chemistry, and that's John Dalton in 1803. And John Dalton first really proposed this modern understanding of an atom. And the atom being the smallest particle that couldn't be broken up or any further. So, and it was spherical and just basically was something that we couldn't break up anymore. Then a scientist, J.J. Thomson, in 1897 discovered the electron. And as a result of his discovery of the electron, he was able to come up with a new model for the atom. And that was that it was a sphere, like John Dalton's model, but the sphere was positively charged and spread throughout the sphere were electrons. And these electrons had a negative charge. And this was called the plum pudding model. That was after now quite outdated pudding, which is a round pudding, not dissimilar to a Christmas cake, and with currants in it, or pieces of fruit, pieces of plum in it. So that's where that name came from. And this model stayed as it was for about 20 years or so, until this scientist came along in 1909, Rutherford. And Rutherford did an experiment which we're going to talk about in a minute, and he showed that actually the positive part of the atom was very, very, very small and very dense, and that these electrons must also have been spread out around it. So, and we called this the nucleus, and we know that it has a positive charge and it's also very dense. And the fact that the rest of the atom isn't very dense at all. So the difference between Rutherford's model and the previous two models is that these assumed that that the atom was quite a dense sphere and filled up with some sort of matter, whereas Rutherford showed that actually the atom, the middle of the atom, was where almost all of the mass was, and then so this was called the nuclear model. Obviously, nucleus is a word that denotes something being in the centre. So we've got a positively charged nucleus here, and we've still got our negative electrons. We then have a scientist, Niels Bohr, who was working in the 1920s, and he came up with this planetary model of the atom. So we still have a small positively charged dense nucleus, and that in fact the electrons are orbiting the nucleus, so that's why it's the planetary orbital model. So these electrons are orbiting the nucleus in shells. In 1932 we get a scientist called James Chadwick, and he adds one further addition to the model, and that's he's discovered the neutron. So our nucleus now isn't just made up of one particle, it's made up of two particles, protons, which are positively charged, and neutrons, which are negatively charged. And then obviously we still have the electrons orbiting that nucleus. So we've got protons, which are positively charged, neutrons, which are neutral, and orbiting them we have electrons, which are negatively charged. There was one further change to the Bohr model, which is the Schrödinger model, which was in the again in the later 1920s, and this actually changes our understanding of the electrons orbiting. That is the beginning of quantum mechanics, but that's not something we deal with at GCSE. So this is the model that we think about at GCSE, and it serves our purposes. It allows us to make predictions, and we need to know basically how we got from the Dalton model of a solid sphere all the way up to this Chadwick model. So, just as a quick review, J.J. Thomson, plum pudding model, positively charged sphere with electrons dotted around it. Rutherford showed that actually the nucleus was very small and dense, and all of the mass was located, almost all of the mass of the atom is located in the nucleus, and the electrons are just dotted around it. Bohr added to this and said that actually the electrons are orbiting the nucleus, and Chadwick discovered the neutron. So because the neutron has no charge, it was obviously doesn't really interact with any fields, so that's why it was the last and a relatively late particle to have been discovered. So we need to know something about this Rutherford model as well. So we're going to look first of all at the experiment that Rutherford did, and then how he was able to use that. So the key thing is that Rutherford had a piece of gold foil, and that gold foil was beaten very, very thin, so it was only actually about 2 atoms thick. And then there was a source of alpha particles. Now alpha particles, hopefully you remember from physics, are particles that are helium nuclei, and they're made of 2 protons and 2 neutrons. So the key thing is they have a positive charge, a 2+ charge. They have quite a bit of mass as well, relative to an electron. And around the outside of this experiment was a large fluorescent screen, and the fluorescent screen glowed when an alpha particle hit it. And this is an experiment that actually took days to do. With there was no at the time no ability to get cameras or computers to monitor it. This was people sat watching for days in teams and collecting the results. And what they found was, and this was actually largely expected at the time, that almost all of the alpha particles went through. So loads and loads of beams of alpha particles, and they were seeing spots at this point here showing that the alpha particles had got through, and that was expected because the atoms were because the gold was beaten really, really thin. But they found that a few, not many, but a few of the particles were deflected ever so slightly, and even fewer particles still were reflected backwards. So we'd see a spot there and we'd see a spot there. So what this showed was that the majority of the atom, almost all of the atom, was just empty space. So let's have a look at that here. So I'm actually just going to do this for one single layer of gold, although it was probably 2 to 3 atoms thick. So here's some gold atoms. Here's their, now we understand it, very, very small, very dense, positively charged nucleus. So what's happening, because this is so small, it's less than 1% of the volume of the atom, the chance of a beam of an alpha particle hitting it are very, very low. So we're expecting to see things like this. So the alpha particles, for the most part, because the nucleus is so dense, are just passing through. If an alpha particle happened to get quite close to the nucleus, it would be deflected slightly. Now the reason that happens is our alpha particle is positively charged and our nucleus is positively charged. So as it approaches, it repels each other and it changes the path. And in a very, very few circumstances, remember the chance of this happening is very low, the alpha particle hits the nucleus bang on and then is reflected back. Now this was the most unexpected of all. In fact, one of the scientists said at the time it was like firing a cannonball at a piece of tissue paper and the cannonball bouncing back. And what that showed was that the nucleus was very, 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 very dense, and therefore could reflect the alpha particle back, but that it was very small and occupied less than 1% of the total volume of the atom. So most of the atom is empty space. So this was Rutherford's experiment, and it's actually often called his gold foil experiment. And the key conclusions was most of atom is empty space, and the nucleus is very small and very dense, and also that the nucleus has a positive charge. Okay, that's it.